In the last video, we talked about the MESI protocol and how only one core can hold a modified copy of a cache line at a time. Now we're going to look at something that sounds harmless, but can quietly destroy multi-core performance. It's called false sharing, and it has nothing to do with threads intentionally sharing data. That's what makes it dangerous. Let's start with a simple scenario. You have two threads running on two different CPU cores. Each thread updates its own counter, two completely separate variables. No locks, no communication, no logical sharing. You expect this to scale perfectly, but performance is terrible. Why? Because those two counters happen to sit on the same cache line. That's false sharing. Modern CPUs move memory in fixed size blocks called cache lines, usually 64 bytes. When a core reads or writes a value, it doesn't just load that value. It loads the entire cache line containing it. Now imagine this. Counter A is stored at address X. Counter B is stored 8 bytes later. Both are inside the same 64-byte cache line. Core 1 updates counter A. That cache line becomes modified in Core 1's cache. Core 2 tries to update counter B, but to modify anything inside that cache line, Core 2 must first obtain exclusive ownership. The coherence protocol invalidates Core 1's copy. Now the line moves to Core 2, then Core 1 updates its counter again. The line moves back, and this keeps happening. The cache line ping-pongs between cores. Even though the threads are not logically sharing data, the hardware treats them as sharing because they occupy the same cache line. That's false sharing. It's false because the variables are independent. It's sharing because the cache line is shared, and it's expensive because coherence traffic is expensive. Let's break down what's really happening under the hood. Each write triggers a state transition in the MESI protocol. Shared becomes modified. Other cores are invalidated. Data travels across the interconnect. If this happens thousands or millions of times per second, performance collapses. Instead of doing useful work, the system spends time moving cache lines between cores. Now let's talk about why this matters. False sharing often appears in performance-critical systems, high-frequency trading systems, game engines, parallel simulations, low-latency services, anywhere threads update separate counters, flags, or small structures in tight loops. The code looks correct. There are no data races. There are no logical conflicts. But the hardware doesn't care about logical independence. It cares about cache lines. Now let's look at a practical example. Imagine you create an array of structures. Each structure contains a small integer counter. You assign each thread to update a different element in the array. Seems perfect, but if those structures are small, several of them may fit inside one cache line. So different threads are updating different elements inside the same 64-byte block. You've just created false sharing. The fix? Padding. If you add padding so that each thread's data occupies its own cache line, the problem disappears. Many high-performance libraries explicitly align frequently written variables to cache line boundaries. In C or C++, you might use aligners 64. In Java, you might use special annotations or manual padding. In Rust, you can use reaper, align. The goal is simple. Ensure that independent variables do not share a cache line. Now let's zoom out. Why does false sharing hurt so much? Because modern CPUs are extremely good at parallel reads. Multiple cores can read the same cache line in shared state without conflict. But writes are exclusive. Only one core can hold a modified copy. So write-heavy workloads are especially vulnerable. If multiple cores frequently write to adjacent memory locations, coherence overhead dominates. This is also why read-mostly data structures scale well. Shared state that is rarely modified can remain in shared state across cores. Minimal coherence traffic, minimal overhead. Now let's connect false sharing to scalability. Imagine you benchmark a program with one thread. It's fast. With 2 threads, it's slightly faster. With 4 threads, it gets worse. With 8 threads, it's terrible. You might blame synchronization. But sometimes the culprit is false sharing. The more cores involved, the more frequently cache lines bounce. Scaling fails not because of algorithmic complexity, but because of memory layout. Now let's connect this to the bigger picture of software execution. Inside a single core, pipelines overlap execution. Out-of-order execution hides latency. caches reduce memory access time across multiple cores. Cache coherence ensures correctness. MESI manages state transitions. False sharing creates unintended coherence traffic. Performance in modern systems is deeply tied to how data is arranged in memory. It's not just about algorithms, it's about layout. Now here's an important mindset shift. When writing multi-threaded code, you should think in cache lines, not just variables, not just objects, cache lines. If two threads modify data within the same 64-byte region, they are sharing from the hardware's perspective. Even if your code says they're independent, that's the key insight. Now let's summarize. False sharing happens when multiple threads modify independent variables that reside on the same cache line. Because cache coherence operates at the cache line level, these modifications cause unnecessary invalidations and cache line transfers. The result is excessive coherence traffic and degraded performance. Understanding false sharing changes how you design data structures. It changes how you lay out memory. And it explains why multi-core scaling sometimes fails in surprising ways. In high-performance systems, eliminating false sharing can produce dramatic speedups without changing the algorithm at all, just by changing how memory is organized. If you want to go deeper from here, the next step could be exploring memory consistency models, or looking at NUMA systems where memory locality becomes even more complex. But mastering false sharing is a major step toward writing scalable, multi-core software. And once you see it, you'll start spotting it everywhere.